infinitesimals, as if they were real numbers, and it was appalling. I mean, if you look at the stuff, a mathematician today looking at it say, that's awful. How could you possibly do that? You don't know. I mean, you don't know the limiting series exists. You don't know the series converges. You don't know if this is going to work or not. But Newton was happily canceling deltas off. Finding out the limits with this thing. Yeah, 3 delta over delta is 3, and I'm going to use the value 3, and that's okay. Even when delta goes to 0. And the mathematician is saying, wait a minute, 0 over 0, that doesn't exist. How can you do that? And Newton said, I don't care. I can show what the moon is going to be in 2 weeks, and a celestial motion I can solve. So you can figure out what the rigorous development is. As far as I'm concerned, 3 delta over delta is 3. And that's great. And so there's always been this tension between mathematicians and physicists, and engineers and mathematicians similarly. If you look at the career of Oliver Heaviside, who was a radio engineer, he did all sorts of crazy stuff using kind of seat-of-the-pants mathematics is the best way to characterize it, or ad hoc approaches, which later on the mathematicians went and cleaned it up. Okay? But generally speaking, the physicists have been ahead of the mathematicians in coming up with stuff that they needed to solve systems. And that's what Dirac did. Dirac went and said, I had this function. And the mathematician said, this is not a function. Says, well, I don't care. It works for me. And he went off and did quantum mechanics using the Dirac delta. And then afterwards, people came and cleaned it up. The mathematicians came and cleaned up all the mess and said, OK, it's a limiting series and all this other stuff. But that was done afterwards. Okay. So this is the Dirac delta. And so what can we use? What can we do with it? What we can do is that we can create the analogs of these two equations over here. And again, you might ask, does it make sense or is it meaningful and so on? And the answer is, yeah, sort of. So I'm going to give you the first equation. So this one says xt delta t equals x0 delta t. Okay. So this one's intuitively what we're saying is that the value of x at 0 is going to kind of multiply delta. It's going to be the strength of the delta function if you multiply it out. So it sort of selects the value x0. Okay, it's similar to a selector. Okay, that's what's going on over here, except that it's not x0. It's x0 delta t. Okay, right? I'm not saying xt delta t equals x0. So the homework question basically said, what is xt delta t for the function shown in the for the figure? And of course, at that point, x 0.5 happens to be 0.5. So x 0.5 delta, I'm sorry, I better, okay, let's just forget that for a moment. Let me just tell you the other one. The other one is when you have the shift. So xt delta t minus tau equals x tau delta t minus tau. Okay, so what we're saying is that we are selecting the tau's value of x. You're kind of moving this arrow over here, this arrow that we want onto the tauth element. And obviously it can't be delta t because delta t is going to be 0 there, but delta t minus tau is going to have some value, some undetermined value. So you get x t delta t minus tau is x tau delta t minus tau. And the homework question was, what is x 0.5? And x 0.5 is going to be, or what did it say was x, actually asked for x t delta t minus 0.5 is what I asked for, right? And this is going to be given by x 0.5 delta t minus 0.5, which is nothing more than 0.5 delta t minus 0.5. So that's the answer over there. Okay. Again, it's not probably what you were expecting. You might have thought the answer is 0.5. No, it's not 0.5. No, xt delta t minus is this value over here. So we haven't gotten rid of the delta. It's still there. It's this funny thing which is multiplying the strength of x at that point, which is x 0.5. Okay? Yeah?
Sorry, is there any meaning for this answer? I mean, because at 0.5, the function is undefined yet. So
it is defined. X 0.5.
Delta t is undefined at 0.0.
No, delta t minus 0.5 is defined. Oh, sorry, it's not defined at that point. You're right. It's not defined.
Yeah.
Correct.
Is there any meaning for
There's no meaning. It's a mathematical form, but it's the answer. Okay. It's a bit confusing, and I really don't have explanation for this other than saying that if you consider the limiting series, we can assume what the value is, but at the end of the day, the delta function is this mysterious thing. At that point, it has no value, but the form is this: x 0.5 delta t minus 0.5 is a particular form, and when we integrate it, it'll have value, and I'll show that in just a minute. Yeah.
Isn't it plus infinity? The area of 0.5?
It's is it plus infinity? Well, sort of. I mean, delta is not exactly infinity either. It's this ratio of, it's basically the value there is undefined. It is undefined.
Okay, but the area of this will be...
I didn't say area, I just asked for the value. I didn't ask for the area.
Yeah, sure.
Yeah, the area is going to be 0.5. Yeah, because, yeah, sure, because you're multiplying at 0.5. Yeah. Okay, so I am not going to try and explain, give you an intuition for delta beyond what I have, because I don't have it either, and as far as I know, nobody does. Okay, it's one of those things like, what is e to the power, e to the power j? Okay, I can give you intuition, but it's at the end of the day, you look at it and say that's bizarre. I mean, why would you? What does it mean? Okay. Anyway, we'll talk about e to the j in just a moment, but just right now, this is we are kind of just getting into the form right here. So we plug and chug basically. Okay, and now I can use this to write down the analogs of those two equations, and the analogs of those two equations are going to be, so that first one is already over here, xt delta t minus tau is x star delta t minus tau, which is similar to, I guess I didn't, yeah, so, well, that's a summation. Okay, so we don't have that, but we do have that xt, I'm going to write this down, equals integral minus infinity to infinity x tau delta t minus tau d tau. Okay, so this one over here is sort of like this. Okay, if you compare these two, you find that the similarities there. This is a summation that's integral, but the form is x tau delta t minus tau. That's why I set up this form. Okay, in the discrete case, it's trivial. Okay, it's trivial. In the continuous case, we have this mysterious delta, but if you stare at it long enough, it will hopefully make sense. Okay, and I'll just let you do that at home. And the second equation is that if we can just substitute t and tau, so we get x tau equals integral minus infinity to infinity xt delta t minus tau dt. Okay, because delta is symmetric, delta tau minus t is same as t minus tau, so it doesn't really matter. So we get this one, and these two equations become the continuous analogs of this same equation over here, where we just got xt and x tau, and this will become useful later on. So this equation is confusing actually if you just look at it straight away, right? How does it work? But when you look at this equation, which you do know how it works, that's how I go there. So typically when this material is presented, you start with the continuous time case first, and then you talk about the discrete time later, but I find that it's much easier to understand the discrete first. Okay, the discrete first, because this is really quite easy. And at that point, we are able to go into the continuous time. So that's why I did it this way. At least for me, I find it quite a bit easier to understand. And then finally, we have the analog of the discrete convolution. So I'll write that on over here. So we can compare it, the continuous convolution of the continuous functions xt and yt, and we write zt, which is equal to xt convolved with yt, is given by minus infinity to infinity x tau y t minus tau d tau. And again, we get the same kind of form as over there, x tau y t minus tau, except it's integral, not a summation. Okay, and so these two things sort of are related to each other. And again, I made a jump from going from here to here. I went from the delta to an arbitrary function y. And in the same way, I'm going from the delta, the Dirac delta, to the arbitrary function y. And I'm kind of just defining this to be the case. There is a physical interpretation to this, which I'll give you. And it sort of looks like this. So let's say we have some function xt that looks like that, and we have some function yt that looks like this. Okay, let's say this is yt, this is xt, and this is yt. Okay, what does y minus t look like? Okay, so what y minus t looks like is going to be the mirror image. Okay, so I'm sorry, x doesn't have to be limited in 0, it can be anywhere. So this y minus, this is yt. Y minus t is going to look like the mirror image of this. So this is y minus t, and y minus t is going to have sort of this bump going down like this, and then something like that. Okay, so it's just a mirror image of yt. Okay, so let's take off yt and look at y minus t, and what we want to do, okay, so what am I doing? Actually, it should be xt minus tau. So I can also, so this is yt is also going to be minus tau as well, because I can change the time index from t to tau. So this is x tau as well, and that's y minus tau. So what this integral can be viewed as basically saying that I'm going to take the small portion here and multiply it with the small portion over here, and define the area as a product of those two things, and then I can kind of shift this in this direction and kind of compute these products together. So let's say the support of y were here and this y were here, and this was the support. So this was x was time limited like this from here to here. What would happen is we take this and kind of slide it across. And then in the beginning, we'd have this one and that one, because that's x tau, y, t minus tau, everywhere else it's 0. And as we shift it, we get basically larger and larger overlaps, and we compute the products and compute the areas. Okay, and so we have this notion of this one function fixed, the other one kind of sliding across, and taking the product and multiplying it out. So some textbooks talk about this. Personally, I find this not very intuitive. Okay, it has this image, but it's not particularly intuitive. I find it far simpler to look at the discrete analog and look at the continuous from there. But yeah, that's one way of looking at it, I think. So you had mentioned what is the interpretation, and the continuous case, that's what it is. The discrete case, it's a histogram flipped over and kind of multiplied as well. Okay, and then in the book there is an example of computing the convolution, which I'm going to skip in the interest of time, because I want to cover the complex exponential a bit more in detail. So any questions about this over here? A convolution definition is a bit bizarre. I encourage you to look at the discrete time and then try to figure out why the continuous time looks like that. And the reality is we never compute convolutions ever. Okay, we never compute convolutions. We only go we basically take the transform and do everything in the transform domain, because computing the convolution is a pain in the neck. As you'll see from the example, it's really no fun at all. Okay, and that's one reason why we want to work with transforms, because convolution is something that we have to do all the time, and I'd rather do it in the transform domain. Okay, so before I erase it, any questions about this at all? Okay, so I want to do one piece on signals, and we'll take a break, and then I'll talk about the complex exponential. So signal is just signal is basically a set of data, and usually it's indexed by time. Okay, it doesn't have to be, but it can. We typically assume that the x1, x2, etc. correspond to time instance 1, 2, 3, and so on. Okay, but it doesn't have to be. We can take any series and view it as a signal, as you've seen in there. Okay, so the signals can be classified as discrete or continuous. And the reason why, so discrete distribution, discrete signal is one which has values at specific points in time. So it looks like a staircase. You have it's until this time it's this, and it takes these values over here. So we can identify specific times where the value changes. Okay, so just before it's something, and just after it's something else. That's a discrete one. The continuous one would be something like this. Okay, which would be at all points in time it has a value. Of course, both have values at all points in time, but the value can change at any point in time. Okay, that's discrete. Now, what people typically confuse this is with the digital versus analog. So a digital signal, okay, so if you look at this one, digital signal has only a particular set of values it's allowed to take. It can take only these 4 values. So okay, here's a discrete and digital signal. Okay, something like that. Oops. Okay, and then we can have discrete and continuous signal as well, where the values can be anywhere. We can't really draw these levels. Okay, we can be anywhere in the range. We really have no idea where it's going to be. Whereas so that's discrete and analog. And in the continuous case, we can have continuous and digital. So it moves, but it only have these values over here. So it's kind of hard to imagine really, I guess, what a continuous and discrete symbol is. And certainly continuous and analog would be what you're thinking of. So typically, we are working with these two over here, discrete and quantized, or digital. This is digital. And that's going to be continuous and analog. And discrete and analog can be defined. It doesn't really occur very much. And continuous and digital, I can't think of anything. I don't even know how to draw it actually, because
Computer hardware is, I think it's all digital, but it's continuous. So it's like exponential up and down.
But computer digital systems typically have a clock, and so that's why we call it discrete, because at the clock we're going to have these changes. When the clock doesn't take, all the values are constant.
Yeah, but gate level is just like don't have clock.
Well, the gate levels are going to be continuous, and but they're going to be continuous and digital. That's right, continuous and digital. Right. Okay. So that would be a gate level. So you kind of have but you can have intermediate values. You see, so what makes it analog, right? Because you have a rise time and you have like a settling time, and then that would be not quite digital. That would be continuous and analog. Okay. So we don't really have continuous and digital. So anyway, so those are the two things, and often you confuse discrete and digital because they usually go together, but they're not the same. Okay. All right. And then the other two things that we'll look at are periodic versus aperiodic. And well, periodic means there is a period, obviously, and aperiodic means there isn't one, or not that we know of. And then we have this notion of time limited or time unlimited. Now, all signals are actually time limited, okay, because at some point you run out of time, okay. I mean, essentially, if you die, you don't really care they're unlimited or not. At that point, it's unlimited anyway by your own personal experience. Nevertheless, for mathematical purposes, we usually deal with the time unlimited signals. We assume it goes on forever, okay, whatever forever means. Another infinity you run into, and we don't quite know what it means, but it works. So essentially, there's no limit. Keep going as long as we want. Okay. So the homework question, I guess, was the number of cars that. What happens? What is the number of cars that enter the campus? So, well, consider number of cars entering the university every minute of the day or night. So it's discrete because we have only it's every minute, right? So measuring every minute, so it's discrete because of that. It's a once a minute. It's digital because we have only a specific number of values. You can't have 2.5 cars. So maybe you sort of can if the car were halfway through, but typically you're going to say it entered or not. So we have to make sure that the atom that's on the tip of the bumper was on the right-hand side of the atom that marked the demarcation point of the campus. And those atoms are either going to be to the left or to the right, other than the uncertainty principle. So we can't really be sure. But for all purposes, we can say it's a digital value. Okay, I mean, now that I think about it, what does it mean to enter the campus physically, right? So these two atoms can have a distribution of probabilities of their relative positions. And now that I think about it, you can't actually decide that. So, but if you don't think too much about it, it's true. If you think too much about it, it becomes fuzzy. I don't know. It's aperiodic, hopefully, but you can argue that it's periodic because every day, there's a night period with very few, and there's a daily cycle. But it's but if you again, it sort of looks like this. Hopefully very little at night, and then goes like this. So one could argue it's periodic at some level, but it's not exactly periodic. It's not the same thing repeating over and over and over again. So it's aperiodic, and it's time unlimited because it's presumably goes on forever. Yes?
So did you say it was digital?
It's digital, yeah.
So what if you have like 500 cars coming in at once? Like,
That's a number, right? 500 cars. 500 is a number.
there's no upper limit, right?
No, that's fine. So we can. You're saying there's no range in which it lies. There is a range in which it lies because certainly the capacity of the roadway is limited, right? You can't have a million cars entering within 1 minute. It's not going to happen. So it's limited. Yeah.
I'd like to argue that the way you phrase the question is actually time limited because you use the article the day or night.
Every minute of the day or night. I see. You want to argue that it's time limited because it's a particular day. If that's interpretation, then you're correct. But I'm not going to argue semantics here. It's not even like 0.0 what's 1/4 of 1 point. It's like forget it. Okay. So how many of you have seen this kind of stuff before? You've seen it. Okay. So I know all the nerds in this class. Okay. I believe it's called Jax or something like that, and somebody gave it to me at some trade show many years ago, and it's actually kind of fun. I'm going to show you how to play it. It's what you do, and then if you're really good at it, which I'm not, you can kind of swap your hands, and you can do some funny stuff with it, I guess. And I have to admit that once in a while I play with it, but only when I'm not working at home and stuff. But it's a kind of alternate to the yo-yo, I guess. And I do juggle, and I'll bring in my juggling bag someday to amuse you guys and to wake you up. But the reason I'm bringing it here is because it's a phasor. Okay, here is a phasor, and I don't know if I can. Let me see if I can do it properly. So you can. These are actually two phasors. You can think of the center point as being the of the mutual. There is a center point. One is actually rotating in smaller circles than the other. But if I do it right, you'll find that they'll be exactly centrally balanced. And so what you're seeing is actually, I would say, is a phasor, right? So let's just focus on one of the blue balls, and it's certainly rotating. And if you can imagine that I'm going to move towards you, what's happening is that this phasor, one of the blue points, is transcribing a helix. Okay, do you see that it's transcribing a helix in time? It's a circular motion, if I can get it right. Let's see. Yeah. So here's a if you can, as I walk, the point is transcribing a helix. Okay, and there you go. That's a nice helix. And we have a particular orientation of the helix. It's rotating like this. It's like a corkscrew, if you will. It's a corkscrew that's being traced in time. And in fact, this corkscrew that's being traced in time is the physical significance of e to the j theta. Okay, this is e to the j theta in real life. So when I got this toy, I was playing with it and said, "Oh my goodness, this is exactly a complex exponential." Okay, now you know you're a nerd. Okay, when you see a toy and you say that's a complex exponential. And then you can do some other fun stuff which are actually phasor calculus and algebra, which I won't get into. But the basic stuff, there we go, is a nice rotating thing. And if I change the amplitude over time, as I'm doing over here, and let me try and show that to you. So I have this small rotation. I can make it larger and larger and larger. I could actually make this exponentially large over time. What I'm doing is I'm modulating the helix. So the helix kind of starts out small, and here's a small helix, and it's getting larger and larger and larger over time. Okay, so that's demonstrated over here. And the third thing I want to show, and I'll see if I can do it or not, because this requires advanced. Let's see if I can do it or not. What I'm trying to do over here is to get them to counter-rotate at the same time. And if anybody has seen Samoan fire jugglers, has anybody seen Samoan fire jugglers? These are guys with pots with fire in them, and they kind of do this circles at the same time. I'm going to try and simulate this with these phasors over here. Okay, but it turns out to be, I tried practicing for this in class, I didn't really quite succeed, but I'm going to let you assume that I could do it. And if maybe on YouTube there's a video about this, what you're trying to do is to look at two things that are rotating at the same time in opposite directions like this, okay? Right? And when you do that, you get this like so, and then the other one like this, and let's say the equal magnitude. At each point in time, let's take the vector sum. So I have this over here. So I'll draw the vector like this and a vector like that. So here are their real, these are the projections on the x and y axis. Clearly, the projection on the x axes are equal and negative. So they cancel out. And what you get is twice. You get twice the value on the y axis. How much is that going to be? It's going to be basically 2 sine theta, right? If the rotation, angular rotation is going to be omega, it's going to be 2 sine omega t. Is going to be the magnitude over there. So what does it mean when t is 0 over here? Then we are going to find that both the values are 0, so the projection is 0. Okay, and we go up a little bit, that goes up a little bit. Sorry, I'm going like this. So I go up a little bit, that goes up a little bit. Those things go away. The x projections cancel each other out, right? If I had counter rotations. So what's left, if you sum up these two rotating phasors, is actually something that goes up and down on the vertical axis. Similarly, if I choose a different sum, I can cancel out the y values. And the way I do that is to take, let me see, I have to remember how to do this. Let's say we take a circle like this. And so I want to essentially make sure that the y values cancel out. So if I take these two guys, and I have one going, I take a phasor that's like this, and then a phasor like that, the y values cancel out, and the x, and if I subtract one from the other, the y values cancel out, the x values double, and I get something like that. So if I subtract these two guys, right? If I take this phasor value and subtract this from it, I'm adding from it, right? No, I'm subtracting from it, and then the this negative value doubles up, and the y values go away, or maybe not. Okay, I'll do the math. I'm better at math than at drawing circles on the screen. But at any rate, the intuition is first that we have a rotating phasor, and second, if we add rotating phasors up, we can cancel out the x or the y projections if we do it properly. And that gives us really the figures that are in the handout and that I wanted you to draw. So it took me 4 hours to draw these 6 figures. So you may as well look at them for a few minutes at least. So what I'm trying to show over here is the signal k e to the s t, where s is equal to sigma plus j omega. Okay, and so we get k e to the sigma plus j omega t, which we write down as k e to the sigma t e to the j omega t. And so let's say Right, so this is the signal over here. Okay, so let's take the simplest case where we just set s equals 0. Let's say case 1, s equals 0. This implies e to the st equals 1. So this expression k e to the st equals k. Okay, that's a constant. It's just a constant, doesn't change. And that's sort of the degenerate case of this, where this kind of goes away. And if you look at figure 7a, look at what's going on. So the x-axis is the real axis. The y-axis is the imaginary axis. So this is but we added a z-axis over here, which is time. And so the plane that's closest to us in some sense, this plane over here is the standard complex plane, but we have the complex plane going through time. And so we choose a particular value of k, which is going to be a real value of k. If k is real, let's assume k is real, then this is a real value. So it's going to be on the real axis, and it always stays that way through time. It doesn't change, okay? So it's a real value through time. That's a constant. So this is the graph of e to the st when s equals 0. Yeah?
It is a 3-dimension space.
Yeah. 3-dimension space. So I have the complex plane, and then sort of in the z-axis I have time. Okay. Yeah. So I'm trying to show the complex plane. I don't know how well I've succeeded, but that's and the two shaded planes are the real versus time and the imaginary versus time on the axis. Okay. Now let's take the second case. In the second case is where omega equals 0. Okay. So omega is the angular velocity. Okay, the angular velocity equals 0. Then what do we get? What we get is basically k e to the sigma t, and that's all we have because omega equals 0, and that drops out. So we just k equals sigma t. So what happens over time? Basically, k is some constant. Okay, let's for the sake of argument just say k is 1. Okay, keep it simple. It's an exponential that's growing over time. Okay. At the rate of sigma. So let's say e to the power 2 is e squared. So if you have the function e to the 2t, for example, it's growing exponentially with time, right? And so when you normally draw exponential, we draw it like this. E to the 0 is 1, and then this, let's say e squared, then this is going to be at time 1, it's going to be e squared. At time 2, it's going to be e to the power 4, and so on. So this is sort of the exponential, the standard exponential you've seen, except that here, and I'm not going to draw this because it's the figure, you can take a look at it. If you look at figure 7b, you'll see what it looks like. It stays in the real plane, so it's not going to leave the real plane. That's why I drew the real plane. And it's growing with time, okay, because positive time is away from you, and you see that it's growing exponentially over time, okay? And this has no imaginary components whatsoever. It's just growing over time, okay? All right, now let's take a little bit more complicated case. And here what we're going to do is we're going to sum up a couple of exponentials. So we said sigma equals 0, so just ignore that part. And so we have k to j omega t. What we'll do is we'll set s equals plus minus j omega. So we have now two counter-rotating phasors, right? And then we get the sum k cos omega t plus j sine omega t. This is just from Euler's formula, plus cos omega t minus j sine omega t, which is equal to 2k cos omega t, because the j's cancel out. So what I'm saying is that if we take these two phasors, and these are actually counter-rotating phasors, because we can think of one as having a positive frequency, one having a negative frequency, right? Plus j omega is going to be positive frequency, which means anti-clockwise, and minus j omega is going to negative frequency, it's going to be clockwise, okay? By definition of the angular frequency. So if you set these two, this is what I mean by having two counter-rotating phasors, and if I add them up, what happens is that the x components go away, okay? And sorry, the y components go away, and I get this one over here, 2k cos omega t, okay? And when you do this, so this is like these, the one phasor is one phasor is kind of going like this, the other phasor is going like that, okay, and the I choose them so that the y components cancel each other out, and you get doubling, okay, which is like those two rotating things, and I want to cancel out. In this case, cancel out the x, here cancel out the y. So this is real. That's the important part. It's real, okay, because the complex components are cancelled out. So that's what you get by having these two phasors. Okay, the phasors are rotating in the complex plane. Okay, they have complex value and a real value, but by choosing the values just right, the complex values cancel out. So what's left is a real. And so you look at 7c, you find a sinusoidal, okay, which is 2k cos omega t, but nothing on the imaginary plane. It's all gone away. It's cancelled out just right. And that's why we get this over here. So that's why I wanted to show you the demo of the two counter-rotating helices. So if you take two counter helices and you set them up just right, you can get a real out of it, which has no imaginary component, which is kind of interesting because we have certainly a complex exponential, but the sum of two complex exponentials gives us a pure sinusoidal real oscillation, okay, and that's important. Okay. All right, so now we can make this very simple. If sigma is non-zero, what happens? You get the sinusoid in the real plane, and we're going to blow it up. So we sort of take, if you look at 7d, we're going to essentially multiply 7b and 7c together. Okay, so when it's less than 0, it diminishes, and when it's greater than 0, it grows exponentially. Okay, and that's what you're getting over here. Okay, so in 7d, we have the sinusoid, but it grows larger and larger over time. Okay. How many of you have seen the collapse of the Tacoma Narrows Bridge, the video of the Tacoma Narrows Bridge collapse? Most of you have seen that. It's a bridge, and you see it's a sinusoidal oscillation, and the sinusoidal oscillations are growing greater and greater over time until the bridge basically collapses. Okay, that's exactly 7D. Okay, and when we talk about systems, we'll actually see the exact conditions under which the Tacoma Narrows Bridge collapse happens. Basically, the exact manifestation. But it's a real sinusoidal oscillation. It turns out that it's the sum of two complex phasors. Okay, so now we're going to get a bit more fancy. What we're going to do is we'll take just one thing. So we'll take sigma equals 0, and it's all we have. So we have basically got two 2 cos omega t plus j, sorry, what am I doing here? Sigma equals 0. We just get cos omega t, k cos omega t plus j sine omega t. Okay, this is a helix actually, and that's what's shown in 8a. And to see why it's a helix, what you need to do is to go home and get a corkscrew, okay? Hopefully you have a corkscrew lying around somewhere, and take a flashlight and hold it like this. It's a projection of the helix on a plane, and what you'll see is a sinusoid, okay? The projection of the helix on a plane is basically saying, okay, I'm going to take either this one or that one, okay? And interestingly enough, if you take the projection this way and the projection this way, you'll find that those two projections are 90 degrees out of phase, okay? If any corkscrew, and if you stare at it enough, and believe me, I have, you'll find that the two projections are 90 degrees out of phase because cos is just sine that's 90 degrees out of phase, okay? Cos pi by 2 plus x is sine x. So we're 90 degrees out of phase. So the corkscrew is going to have projections on the real and the imaginary axis. If you look at this carefully and imagine a flashlight shining down, you'll find the projection on the real plane, real time plane and the imaginary time plane, and this will actually be sinusoid. So in fact, 7c is nothing more than 8a with kind of the flashlight projecting down onto the real plane, okay? And what do we do by projection? We get rid of the j component. We just have k cos omega t, which exactly is 7c, okay? And the same thing is true on the complex plane as well. If I shine a flashlight, or here's the other thing I can do. I can take this and rotate it 90 degrees because cos is just sine rotated 90 degrees. So rotate 90 degrees, I get the imaginary plane here, okay? And then I get the projection imaginary plane, which is going to be sine omega t. This goes away. So just rotation gives you the exact same thing. So you take the thing and rotate it, And you get, yeah, sure, I get a sinusoidal on the imaginary time plane, which is the same plane over here. So the real time plane becomes the imaginary time plane over here. And then the last case is going to be nothing more than the product of 7b and 8a, where we have the where we have sigma is non-zero, so we're kind of modulating it. So the helix grows with time, which is what it was doing with that toy where the helix was growing larger and larger over time. Okay, but now it has both real and complex components. If you take the real projection, it will look like 7D. The real projection is going to be an exponentially growing sinusoid, and if I turn it that way, the imaginary projection is also going to be an exponentially growing sinusoid. Okay. So all of these come from just k to the st, where we were allowed to add up a couple of phases if we want to. We're allowed to choose what s looks like and what k looks like and what sigma and omega sigma looks like and so on. And by just playing around with this, we get all these different shapes, and that's really the heart of a lot of different things. And I'll just stop by saying that in general, if this describes evolution of a system, we want the system to not go bigger and bigger over time. Okay, we want it to just die down. Okay, if you kick something, you want to give it a push. You want the thing to oscillate and then kind of die down. If you push something, it goes like that. Bad. Okay, this one is okay. It's marginally stable. Okay, so this one is unstable. This one is marginally stable, and this one is good. Okay, so you pluck a guitar string. Imagine a guitar string. You pluck it, and it brings bigger and bigger oscillation, and the guitar collapses and falls into pieces. It's a bad design. Okay, don't do it. Okay, when you pluck a string, it vibrates nicely for a while and then dies down exponentially. You know, at the e to the minus sigma t. Good. That's a good design. So all of control theory reduces to this. Okay, we find out whether the system is this, bad, okay, good. That's really, in decays, that's really very good. So, okay, that's all. Thank you.